Could you build a tower without cranes? Today, when we look at city skylines, we see the silhouettes of construction cranes, without which it is impossible to imagine the construction of even the simplest building. How did our ancestors in the Middle Ages, without hydraulics, electricity, or internal combustion engines, erect grandiose cathedrals and castles whose spires still pierce the sky? Each stone raised to a height was the result of complex and coordinated work, hidden from the eyes of the casual observer. Behind the majestic facades of Gothic cathedrals and the impregnable walls of castles lies the quiet feet of the engineers and builders of the past. Watch the video to the end, and you will learn how simple laws of physics, embodied in wooden ropes, made it possible to lift multi-ton blocks to dizzying heights. At the heart of every great medieval structure lay not a chaotic pile of stones or spontaneous construction, but the carefully considered ideas of one outstanding person, the master builder. The entire future cathedral, with all its arches and spires, was first conceived and fully constructed in his imagination. It was this initial concept, this intellectual model, that served as the foundation for all the subsequent years of labor by thousands of people. This man was much more than a simple worker. He masterfully combined many roles, from a far-sighted architect to a meticulous engineer and an authoritative leader of the entire project. His main truly invaluable tools were not a rough hammer or pickaxe, but an elegant compass, a precise ruler, and carefully prepared parchment. On these seemingly simple tools, he meticulously created sketches and drawings of future architectural masterpieces that would change the face of entire cities. Before the first, even the smallest stone was laid in the foundation of a future building, the master builder spent countless months, and sometimes long years, in continuous and deep calculations. This quiet and invisible work was an intense intellectual battle with the forces of gravity and the resistance of materials. With filigree precision, he determined the optimal thickness of load-bearing walls, the strategic location of all supporting elements, and the ideal shape of grandiose arches. In his calculations, he relied both on the centuries of experience accumulated by previous generations and on his own deep knowledge of geometry and statics. Any error, even the most insignificant, in these critically important calculations was absolutely unacceptable. An incorrectly calculated lateral thrust of the arch could result in the inevitable and catastrophic collapse of the entire multi-ton structure, decades or even centuries later. Many of these vital drawings were not created on ordinary paper, but in colossal life-size form directly on huge, specially leveled plaster floors called tracing grounds. These squares, often located in a separate large room, were a sacred place where the abstract geometry of the project first took on real, tangible dimensions. With astonishing, almost mystical precision, the craftsman drew the complex contours of arches, elegant window openings, and ornate ribbed vaults on these giant fields. Every line on such a floor was calibrated to the millimeter, becoming the standard for the entire construction. These gigantic, seemingly animated diagrams then served as flawless templates and instructions for the stonemasons. With their help, the craftsmen carved each individual stone block with minimal deviations from the specified ideal shape. The work of the master builder was shrouded in deep mystery and sacred reverence, and his unique and irreplaceable knowledge was passed on only to carefully selected and most capable apprentices. These chosen ones proved their dedication to the craft over many years before gaining access to the secret calculations and construction secrets. They swore an oath to keep these secrets because they were the ones who ensured the prosperity of the entire guild. He was not just a leader, but a true guardian of invaluable professional secrets that allowed his workshop to maintain an exclusive monopoly on the construction of the most complex structures throughout Europe. It was his genius vision, his impeccable intuition, and his mathematically precise calculations that sometimes transformed the complete chaos of a huge construction site into perfect harmony. Thus, under his leadership, the majestic tranquility of powerful stone arches soaring upward was born. Just think how incredibly accurate such complex architectural and engineering drawings could be, created without a single modern computer program or automated calculations. All this was achieved by relying solely on the sharp mind, keen eye, and skilled hands of a medieval genius. Share your profound thoughts and reflections on this in the comments below this video. Majestic towers and cathedrals began their long journey as silent, immovable rocks, often located tens or even hundreds of kilometers from their future construction site. The process of quarrying stone in the Middle Ages was incredibly labor-intensive and required not only enormous physical strength from the workers, it required a deep, almost intuitive understanding of the internal structure and properties of the rock. For this titanic work, people used the simplest and most uncomplicated tools: heavy iron wedges, massive sledgehammers, and long wooden levers. The skill lay not in the power of the tool, but in the ability to use it correctly. It was knowledge, not technology, that made it possible to separate the perfect block from the rock. First, experienced stonecutters carefully examined the rock to determine the lines of natural cracks and the direction of the rock layers. This ability to read the stone was key, as choosing the right place to split it saved hundreds of hours of work. A series of deep, even holes were then carved out along these marked lines. Wedges made of dry, seasoned wood, most often oak, were tightly driven into the prepared holes. These wedges were then generously and continuously watered, starting a slow but inevitable process. Swelled by moisture, the wood created enormous internal pressure, which slowly but surely broke off the multi-ton monolith from the parent rock. Immediately after being separated from the rock, the giant stone block underwent initial, rough processing right in the quarry. A special team of stonecutters removed all excess and unnecessary weight, giving the stone the approximate, rough shape of the future building element. This stage was critically important for all subsequent logistics. Such on-site processing made subsequent transportation much easier and saved enormous effort on the part of people and animals. It was much easier to remove a ton of excess stone in the quarry than to drag it across fields and forests. This was the first and most important step in optimizing the entire construction process. Delivering the processed stone to the construction site was one of the most difficult and large-scale logistical tasks of the entire era. Blocks weighing several tons were loaded with incredible difficulty onto massive wooden sleds or special heavy-duty carts. These carts were equipped with solid wooden wheels reinforced with iron for strength. Large teams of oxen were used as the main pulling force, slowly, step by step, dragging their precious cargo. They moved along primitive, barely passable roads, crossing rivers, hills, and swamps. This stage of the journey could take weeks or even months. To move particularly heavy and oversized blocks over short distances, an ancient but very effective system of wooden rollers was used. First, the edge of the stone was lifted just a few centimeters using long levers. Short, thick logs were immediately placed under it, and then the block was pushed forward. As it slowly moved forward, the workers immediately moved the rollers that had been freed up at the rear forward. This created an endless moving track that significantly reduced friction. This method required perfect coordination and teamwork. Water transport was the most efficient and preferred method of long-distance transportation. The stones were loaded onto flat-bottom barges and floated down rivers, which made it possible to deliver building materials from the most remote quarries. Many great cathedrals were deliberately built on the banks of navigable rivers for this very reason. However, this method required the creation of a complex and expensive infrastructure, including sturdy piers and powerful lifting mechanisms, both in the port and in the quarry. In addition, navigation was highly dependent on the season and the water level in the river. It was an effective but very difficult method. The process of loading a stone block onto a barge and then unloading it required precision and the coordinated work of dozens of people. Simple but reliable wooden cranes were used for this purpose, which were powered exclusively by muscle power. Any mistake or haste at this point could lead to the loss of valuable building material. The fall of a multi-ton block could not only damage the stone itself, but also completely destroy the pier or sink the transport vessel. Therefore, the most experienced and responsible craftsmen supervised this operation. The price of a mistake was too high. Which of these methods do you think required more skill and ingenuity? Carefully splitting the rock in the right place, or safely delivering a multi-ton block without damaging it? Write your opinion in the comments, because each stage was ingenious in its own way. But how could this stone be lifted to the height of a 10-story building once it was finally delivered to the construction site? We will discuss this in the next chapter, where we will reveal the secrets of the most impressive mechanism of the Middle Ages. The central element and, without exaggeration, the technological heart of any large medieval construction project was not a person, but an amazing mechanism. We are talking about a giant lifting crane, widely known as a treadmill or squirrel wheel. This simple but absolutely ingenious device allowed the elementary muscular strength of a walking person to be converted into colossal, unprecedented lifting power. The entire structure was a huge, awe-inspiring wooden wheel mounted on a sturdy frame. Inside this giant drum, workers walked monotonously and rhythmically, like squirrels in a wheel. It was their simple and natural movement that set the entire complex system in motion, lifting multi-ton loads. The diameter of such a wheel was truly impressive and could reach 4 or even 5 meters, which is comparable in height to a modern 2-story house. It was this large size that created the most powerful lever, multiplying the effort of the people walking inside many times over. Several people walking in unison inside the wheel caused it to rotate slowly but inexorably. This rotation was transmitted to the central axis, which in turn wound a thick and durable hemp rope around itself. At the other end of this rope, a load intended for lifting was securely attached. It could be a massive stone block or oak beam, or a large container with vital mortar. The entire principle of operation of this mechanism was based on the simplest laws of mechanics known since ancient times, but its practical effectiveness was truly remarkable. Just 2 or 3 people working inside the wheel could easily lift a load weighing up to 1.5 tons. They lifted this weight to a height of several tens of meters, which was unattainable for any other technology of the time. Reinforced cranes were used to lift even heavier and more massive blocks, such as support columns or keystones of arches. These structures were equipped with 2 such wheels, working synchronously on one axis. This system effectively doubled the power of the mechanism, allowing it to work with the largest elements of the structure. Such a crane was not located on the ground, but usually on the uppermost tiers of the building under construction. It was installed on temporary but very sturdy wooden platforms, specially erected for this purpose. From there, it could serve the entire upper part of the construction site, delivering materials precisely to the place of installation. As the stone walls grew, the crane had to be raised higher and higher. To do this, it was carefully dismantled and then lifted piece by piece to a new, higher level using a system of blocks and hand winches. In this way, the lifting crane grew along with the building, always remaining at the very center of construction activities. The work itself in the treadwheel was extremely monotonous and required exceptional physical endurance from the people involved. Workers had to walk inside the huge wooden structure for hours on end. Their measured and rhythmic steps set the pace for the entire construction, on which dozens of other craftsmen depended. However, despite its monotony, it was this machine that made it possible to build as high and as fast as was possible in those distant times. It was the engine of progress that pushed architecture upward toward the heavens. Without it, the construction of high-rise buildings would have taken much longer. It should be noted that there were also various more sophisticated designs of such cranes. Some of them had a single long and immovable boom, which limited their functionality. Others were equipped with a complex rotating mechanism that allowed not only to lift, but also to carefully move the load in a horizontal plane. This technical flexibility made the treadwheel a truly versatile and indispensable tool on any construction site. The ability to position loads accurately significantly sped up the work of bricklayers and reduced the need to move blocks manually at the top. It was the pinnacle of medieval lifting technology. Safety when working with such a powerful mechanism was absolutely paramount and of the utmost importance. A sudden break in the rope or failure of the load-bearing axle could have truly catastrophic consequences. Therefore, the ropes and all the crane's components were regularly and thoroughly inspected by experienced craftsmen. The wooden parts of the crane itself, especially the supporting frame and axle, were made from the strongest and most durable types of wood, such as oak. In addition, there was a ratchet system that prevented the wheel from rotating backwards under load. These precautions were vital on a dangerous construction site. As a result, the treadwheel became a true and vivid symbol of engineering thought throughout the Middle Ages. It clearly demonstrated how a simple but clever mechanism could multiply human physical capabilities many times over. This invention embodied the idea that intelligence and knowledge of the laws of nature are stronger than brute force. Without this simple but ingenious invention, we would never have seen the soaring spires of Gothic cathedrals. It was this invention that allowed architects to realize their most daring and ambitious designs. The silhouettes of medieval cities were literally drawn by the movement of these great wheels. The powerful treadmill provided the main and continuous driving force on the construction site. However, the real secret to lifting extraordinary weights was the ingeniously simple system of blocks and ropes. This system, known as a pulley, allowed the force applied by a person or mechanism to be multiplied many times over. This device had been known since ancient times, but it was medieval engineers who brought its use to absolute perfection. They learned to apply it on an unprecedented scale, lifting multi-ton loads to enormous heights. Without this simple mechanism, Gothic cathedrals would never have been able to reach their heavenly spires. At its core, a pulley is a carefully designed system of several movable and fixed blocks through which a long rope is passed in a special way. The fixed blocks attached to a support change the direction of the pull, while the movable ones, attached to the load, provide a gain in force. Each additional movable block in the system theoretically doubles the applied force. Thus, a load weighing 1 ton could be lifted with a force equivalent to a weight of 500, 250, or even 100 kilograms, depending on the complexity of the system. This turned unliftable monoliths into controllable building elements. This principle opened up virtually limitless possibilities for architects. Of course, according to the golden rule of mechanics, the gain in strength was inevitably achieved at the expense of a proportional loss in distance. To lift a load 1 meter using a pulley block with 4 blocks, workers had to pull 4 meters of rope. The work became much slower, but most importantly, it became possible in principle. This slow and majestic ascent also provided the added benefit of increased control and safety. Workers had more time to notice problems and coordinate their actions. Quick jerks were out of the question here, giving way to smooth and measured movements. The blocks themselves were made from the strongest and hardest woods, such as oak or ash, capable of withstanding enormous pressure. Their bodies were often reinforced with iron strips for added strength. Inside the block, a pulley rotated freely on a wooden or metal axle. This pulley was a wheel with a deep groove along which the rope slid smoothly. The quality of these seemingly simple parts directly affected the overall efficiency and safety of the entire lifting system. A well-lubricated axle and a smooth pulley significantly reduced the destructive force of friction. The ropes for the pulleys were woven from hemp, an extremely strong and wear-resistant plant fiber. The thickness of such a rope could reach the diameter of a human hand, and its strength was sufficient to withstand a breaking load of several tons. The creation of such ropes was a separate, very important, and complex craft. Master rope makers worked in long workshops, twisting thousands of thin fibers into a single monolithic and reliable rope. People's lives and the safety of expensive materials directly depended on the quality of their work. A reliable rope was worth its weight in gold on a construction site. By combining the continuous traction of the treadwheel with the multiple force multiplication of a powerful pulley block, builders obtained a lifting mechanism of incredible efficiency. The crane acted as an engine that provided constant force. The block system was the transmission that converted this force into the power needed for lifting. This synergy of two simple technologies made it possible to lift even the most massive architectural elements to great heights. Stone blocks for arches, giant oak beams for roofs. All of this conquered height thanks to this ingenious union. It was a triumph of engineering thought over gravity. However, the use of a pulley system required precise and accurate engineering knowledge. The master builder had to determine exactly how many blocks were needed to safely lift a particular load. In doing so, he took into account not only the weight of the stone, but also the friction in the system and the ultimate strength of the rope used. An error in these calculations could be very costly, and the price was high. An insufficiently powerful system would simply not move the load, resulting in a loss of time. But overloading the system could lead to rope breakage and catastrophic consequences. Imagine the faith that medieval workers had to place in these simple hemp ropes that lifted entire rocks above their heads. How strong do you think these ropes had to be to withstand such weight? But lifting mechanisms are only half the battle, because it's not enough to simply lift the load. In the next chapter, you'll learn how builders created a safe working space for themselves at dizzying heights. No high-rise construction in the Middle Ages would have been possible without a complex and large-scale scaffolding system. These temporary structures, which enveloped cathedrals and castles, were not just a support for workers. They were a multi-level working platform, a transport artery, and a framework for the entire wall construction process. Scaffolding was made entirely of wood, most often from long, straight trunks of coniferous trees. The base consisted of vertical posts connected by horizontal beams and diagonal struts for rigidity. All connections were made using ropes or wooden wedges. One of the key features of medieval scaffolding was its integration with the wall under construction. Builders left special through holes in the masonry, called sockets. The ends of the horizontal beams of the scaffolding were inserted into these sockets, which gave the structure incredible stability and strength. As the walls grew, the scaffolding was built up tier by tier. Plank flooring was laid on the horizontal beams, creating safe and wide working platforms. Workers could move around these platforms, bring mortar, and install stones. The scaffolding served not only for people, but also for transporting materials. Simple hoists, chutes for lowering construction debris, and guides for ropes from large cranes were installed on them. In fact, the scaffolding was the lifeblood of the entire construction site. The construction of such large-scale wooden structures was a complex engineering task. It was necessary to accurately calculate the load, ensure stability, and provide routes for the movement of hundreds of workers. Craftsmen specializing in scaffolding were highly valued. After construction was completed, the scaffolding was dismantled, and the holes in the walls were either filled with stone or left open. In many medieval castles and cathedrals, these holes can still be seen today as silent witnesses to the grand construction process. Sometimes the scaffolding reached monumental proportions, completely concealing the building under construction for decades. For the city's residents, the sight of the cathedral shrouded in a complex web of wooden beams was a familiar sight, symbolizing the continuous process of creation. Powerful lifting mechanisms carried rough and shapeless stone blocks to dizzying heights. However, their further transformation into elegant columns, intricate capitals, and architectural decorative elements was exclusively the work of stonemasons. These highly skilled craftsmen possessed an arsenal of diverse hand tools, each with its own unique and specific purpose. Their delicate work required not so much brute physical strength as absolute precision, incredible patience, and an almost mystical feel for stone. A stonemason had to understand the internal structure of the rock in order to direct his blows with maximum efficiency. It was this intuitive knowledge that distinguished a true master from a mere apprentice. The main tools for the roughest primary processing were a heavy hammer or sledgehammer, as well as various types of steel wedges. With their help, large excess pieces were chipped off the huge block, giving it its most initial, approximate shape. This work required not only considerable physical strength, but also the ability to accurately predict how the stone would behave under a strong impact. Each blow had to be measured and precise, because one wrong move could create an internal crack that would ruin the entire expensive block. The craftsman studied the stone for hours before striking the first blow, finding its weak spots and lines of stress. This stage laid the foundation for all the subsequent, more delicate work. For more delicate and precise work, they used a mallet, a special wooden hammer, and a whole set of different chisels and gouges. The blow of a wooden mallet was softer than that of a metal one, which allowed for very controlled and not too strong blows. This prevented accidental splitting of the stone and allowed work on fragile details. The varied shapes of the chisel blades made it possible to create perfectly flat surfaces, cut deep grooves, or execute the most complex and ornate patterns. The craftsman constantly changed tools, using a wide chisel for leveling and a thin one for drawing the smallest details. This process resembled the work of a sculptor slowly freeing a form from its stone prison. For the final leveling of the stone surface, a special toothed hammer called a bush hammer was often used. Its working surface was densely covered with small pyramidal teeth. When struck, they left a characteristic, evenly rough texture on the stone, removing all traces of the chisel. After such thorough processing, the surface became perfectly flat and ready for laying. Depending on the task, the surface could be left rough or polished to a shine with sand and water. This final finish gave the stone a finished and noble appearance. The absolute accuracy of all the work was ensured by simple but effective measuring instruments. A wooden or metal square was constantly used to check the perfection of right angles. A compass was indispensable for accurately marking arcs and circles, and a simple plumb line was the main tool for checking the verticality of all surfaces. Despite their primitiveness, these simple devices allowed for incredibly high precision. The margin of error was often less than a millimeter, which is comparable to modern machine processing. It was this precision that ensured the density and strength of the entire masonry. Stonemasons very often worked according to pre-prepared wooden or lead templates. These templates exactly repeated the contours of future architectural details and were made in strict accordance with the master builder's drawings. Applying such a template to the surface of the stone, the master marked the contours of the future product and then carefully removed all excess material. This method ensured that all elements of the same type, such as stones for a single arch, would be absolutely identical. This ensured a perfect and seamless fit of all elements of a complex structure. The use of templates was the medieval equivalent of mass production. The stonemason's workplace, known as a lodge, was usually a small wooden shed. Here, the master could work comfortably in any weather, protected from the scorching sun or rain. His personal tools, numerous templates, and stone blanks were stored in the lodge in strict order. These lodges were often combined into large cooperatives, becoming the center of professional life. Here, experienced craftsmen not only worked side by side, but also exchanged invaluable experience. It was in the lodges that young apprentices were trained and learned the secrets of the craft.
Focus on the grain here.
Which tool do you think was the most important and indispensable for a medieval stonemason? His hammer or his square? Write your opinion in the comments. We are very interested to hear your point of view. The stones are ready, their shapes are perfect, but how to join them into a single whole so that the wall will stand for 1,000 years? In the next chapter, we will reveal the main secret of medieval cement. Perfectly crafted stones were only individual pieces of the puzzle. To assemble them into a strong and durable wall, a reliable binding agent was needed. In the Middle Ages, this role was performed by lime mortar, the production technology of which was inherited from the Romans and improved upon. This mortar was not just an adhesive, but an active component that ensured the strength and flexibility of the entire structure. The main component of the mortar was lime, which was obtained by burning limestone in special kilns. This process required maintaining a high temperature for several days and was very energy intensive. The resulting quicklime was then mixed with water, slaked, resulting in a plastic mass. To give the mortar strength and volume, a filler was added to the slaked lime, most often pure river sand. The proportions of lime and sand were carefully selected depending on the purpose of the mortar. More durable compositions were used for foundations and load-bearing walls, while cheaper ones were used to fill internal voids. The hardening process of lime mortar is fundamentally different from that of modern cement. It hardens not through a reaction with water, but as a result of the slow absorption of carbon dioxide from the air, turning back into limestone. This process, called carbonation, could take years or even decades. It was this slow hardening that gave medieval masonry its unique properties. The mortar remained plastic for a long time, allowing the structure to breathe and adapt to small shifts in the foundation without cracking. Modern hard cement mortar would simply crack under such conditions. The masonry process required a high level of skill. Bricklayers applied a layer of mortar to the bottom row of stones and then carefully installed the next block using winches and levers. It was important to achieve an even distribution of mortar and a minimum joint thickness to ensure a tight fit between the stones. To check the horizontality of the rows, a primitive level was used, a wooden frame with a plumb line. Any deviations were immediately corrected with thin stone wedges placed under the main block. Each row of masonry was carefully checked before moving on to the next. The interior space of the thick walls of castles and cathedrals was often filled not with whole stones, but with a mixture of mortar, rubble, and construction debris. This saved expensive processed stone and sped up construction. However, the outer and inner layers of the wall were always laid out with perfectly fitted blocks. One of the main architectural and engineering challenges of medieval construction was to span large openings, such as windows, doors, and entire cathedral naves. The solution to this problem was the arch, an ingenious structure that allowed vertical loads to be redirected into lateral thrust. The mastery of this principle paved the way for the creation of grand and light-filled spaces. The secret of the arch lies in its wedge-shaped stones, called voussoirs. The central stone at the top of the arch is called the keystone. When a load is applied to the arch, it does not bend it, but compresses the voussoir, transferring the force along the arc to the lateral supports, the piers or columns. To build the arch, the builders first created a temporary wooden support called a centering. This structure precisely replicated the internal curve of the future arch. Using the centering as a template, the masons laid wedge-shaped stones, moving from the supports to the center. The keystone was installed last. This moment was the culmination of the entire process. The keystone wedged the entire structure, forcing it to work as a single unit. After its installation, the arch became self-supporting, and the load from it was transferred to the supports. Once the mortar had gained sufficient strength, the centering was carefully dismantled. This moment was always exciting, as it was then that it became clear whether the calculations were correct. A correctly constructed arch could stand for centuries, withstanding enormous loads. The idea of the arch was developed further into vaults, complex spatial structures that allowed entire halls to be covered. Ribbed Gothic vaults were the pinnacle of engineering thought. Their framework of stone ribs was erected on formwork, and the space between them was filled with lighter stone slabs. This framework system made it possible to significantly reduce the weight of the vault and concentrate all loads at a few points. This, in turn, made it possible to make the walls thinner and cut huge windows into them, filling the cathedrals with light. Without an understanding of the mechanics of the arch, Gothic architecture would have been impossible. Building stone walls and arches was only half the battle. To protect the grandiose structure from the elements, a reliable roof had to be erected above it. The construction of a medieval roof was an engineering marvel in itself, hidden from the eyes of cathedral visitors. Above the stone arches, builders erected a complex system of massive wooden rafters. These giant beams, often made from solid oak trunks, were lifted up using the same treadwheels and pulleys. Assembling this wooden frame at such a great height required exceptional skill and courage from the carpenters. The trusses were designed to distribute the weight of the roof evenly across the load-bearing walls without creating excessive lateral thrust. The complex joints between the beams were made using notches and wooden pegs, without a single metal nail. These structures were so strong that many of them have survived to this day. Lead sheets, tiles, or slate stone slabs were most often used as roofing materials. Lead was expensive but very durable and malleable, allowing roofs of complex shapes to be covered. Lead sheets were cast on site and attached to wooden battens. At the same time as the roofing work, the exterior decoration was also carried out. Sculptors carved stone statues, gargoyles, and decorative elements directly on the scaffolding. Each decorative element was not just a decoration, but part of an overall symbolic program that was understandable to medieval people. The final stage was the glazing of the huge windows. In the Middle Ages, glass was a very expensive material. Stained glass windows were assembled from thousands of small pieces of colored glass joined together with lead bridges. These giant glass panels not only decorated the cathedral, but also told biblical stories to illiterate parishioners. The construction of a single cathedral could take several generations. The craftsmen who began the work rarely lived to see its completion. It was a collective effort that united entire cities and demonstrated not only faith, but also the highest level of technical knowledge of the era. Behind every perfectly laid stone and every arch erected stood an invisible but absolutely pervasive force: perfect organization. Medieval construction was a complex living organism that required meticulous planning years in advance. Without the solid logistical and managerial foundation, even the most ingenious technical devices would not have led to success. This hidden structure was as important a tool as a crane or a stonemason's chisel. It transformed the visible chaos of thousands of people and materials into an orderly and predictable creative process. It was thanks to this structure that the project did not stop, but moved steadily towards its grand completion. At the head of this complex system was invariably the master builder, who was the brain center of the entire operation. He not only created the architectural design, but also personally drew up detailed estimates, hired the best workers, and strictly controlled all supplies. He was assisted by senior craftsmen, each of whom was fully responsible for their own specific area of work, whether it was stonemasonry, carpentry, or blacksmithing. The master builder was the highest and final authority on all technical and organizational issues that arose. His decisions were not questioned, as they determined not only the speed but also the safety of the entire construction project. He determined the strategy and pace of work, coordinating the actions of dozens of different teams. The main production unit on the site was the so-called loggia, essentially a professional guild of masters of a particular specialty. Within each lodge, there was a strict and unbreakable hierarchy, from a highly experienced master to an apprentice and a young student. Knowledge and practical skills were passed on directly in the process of working together, which ensured the unbroken continuity of generations. This guild system guaranteed the highest quality of workmanship and the preservation of professional secrets. Membership in a lodge provided not only stable employment, but also social protection, making craftsmen part of a close-knit brotherhood. The lodge was simultaneously a school, a production team, and a supervisory body. Logistics was rightly considered one of the most difficult and responsible tasks of the entire enterprise. It was necessary to organize the uninterrupted and timely delivery of stone, scaffolding, lime, sand, and iron. Any, even minor disruption in supplies could completely paralyze the entire construction site for weeks. To avoid downtime, managers kept precise records of all materials and planned the necessary purchases months and even years in advance. They created warehouse stocks, looked for new suppliers, and monitored the condition of roads and waterways. Effective logistics was the lifeblood that nourished the giant construction organism. Financing the construction was a separate, equally large-scale and complex task. The money for the construction of a cathedral or castle came from a variety of sources, some of which were unstable. These could be donations from the king, or a local feudal lord, mandatory church tithes, or voluntary contributions from wealthy townspeople. Managing these flows required an entire financial service that kept strict records. Every coin spent was carefully recorded in thick income and expenditure books in order to report to the contributors. Transparency and accuracy in calculations were the key to a continuous flow of funds. The working day on the construction site was incredibly long and physically demanding, starting at sunrise and ending at sunset. Iron discipline was maintained by strict rules and regulations, the violation of which resulted in substantial fines or immediate dismissal. Despite this, working on the construction of the cathedral was considered extremely prestigious and was well paid. The status of a builder was significantly higher than that of an ordinary peasant, as this work required high qualifications and skill. Participation in such a great project gave a person not only a means of subsistence, but also a sense of pride. That is why the best craftsmen from all over the region flocked to the construction site. Perfect coordination between the different teams was absolutely key to overall success. Carpenters could not begin to erect complex wooden frames until stonecutters had prepared the perfect foundation, stones for them. Roofers, in turn, waited patiently for masons to finish building the walls and arches. The master builder, like a brilliant conductor, managed this complex and polyphonic orchestra. He synchronized the work of all the workshops, preventing downtime and conflicts. It was only thanks to his constant supervision that dozens of disparate processes merged into a single harmony of creation. Thus, medieval construction became the greatest triumph, not only of bold engineering thought, but also of ingenious human organization. It was the incredible ability of hundreds of people to work cohesively and selflessly for decades toward a common goal that made it possible to create these architectural masterpieces. These structures continue to inspire genuine admiration and awe in us today. This long-term collective effort was a technology in itself, no less important than levers and blocks. It demonstrated the power of a shared vision and social unity, capable of overcoming any material and technical limitations. Ultimately, cathedrals were not built by stones and mechanisms, but by communities united by faith in a common dream. We have completed our immersion in the world of medieval construction, and it is now clear that the lack of modern technology was not an insurmountable obstacle for our ancestors. On the contrary, it stimulated their ingenuity, forcing them to find solutions that were ingenious in their simplicity. Majestic towers and cathedrals were built not by magic, but by the power of human intellect, multiplied by the laws of physics. Treadwheels, pulleys, levers, and precise calculations transformed muscle power into an effective tool for creation. Behind every architectural masterpiece lies not only the labor of thousands of nameless workers, but also the clear thinking of master builders who saw the future building in every detail. Their legacy is not just stones stacked into walls, but an eternal reminder of the boundless possibilities of the human spirit. What other topics from medieval life and technology would you like to see in our next videos? Share your ideas in the comments. Because history is full of amazing discoveries that are worth telling. And of course, don't forget to subscribe to the channel so you don't miss out on new exciting journeys into the past.